So let's get into some practice with recursion. Like anything else, the more you practice it, the better you get at it. Maybe if you play sports, you play music, you dance, you realize that the more you get practice on it, the quicker you can even be spontaneous. It's easier to make up new dance moves or play a riff when you are really good at your instrument than when you're brand new. And so, um, the reminder I'll say is we're going to try and follow the process. We're going to find the recursive steps. Um, and that's typically going to be because the problem has some recursive features. Not every problem lends itself to recursion. There's going to be one of the assignments where you're going to be asked to solve some recursive problems you did before in looping. And that's because anything that's a loop, generally speaking, can be done recursively. But there's also one that's asking to say what is the median, and that's not a recursive problem, and you don't have to solve it recursively. Not everything is recursive. It's just when there's some iteration going on, that's where things can naturally be recursive. Or if, as we'll see, one of the problems deals with file systems, which are naturally recursive. And when you get to data structures, there's lots of naturally recursive data structures. So let's deal with an easy one here. Um, for example, the math function factorial, and I know easy is in quotes. It might be challenging for you at first to understand it, but hopefully this will help you open the door towards other problems. So the idea of factorial is it's the product of an integer and all of the integers below it, that came before it. So in this example, 4 factorial is 4 times 3 times 2 times 1. And maybe you remember that readily from math, or you saw it at some point and it makes perfect sense. It's really easy to calculate. If I was going to do a loop, I'd say for the number, and while it's greater than 1, or this is Python, so I'd say for range 4, comma 0, comma minus 1, right? And then I'd loop down and multiply them all together. That's a looping way to solve the problem. Nothing wrong with it, just we're practicing recursion now. So how do I see this problem differently? I remember we're trying to identify the base case, figure out how I'm going to resolve that base case, and then move towards that base case. And I have to think about any error cases, any invalid data. So for example, what's the factorial of -1? I mean, there's a meaning for it, but for our problem, we're just going to say anything, let's say less than 2 is going to return 1. So factorial of 0 is going to be 1. Factorial negative 45 is going to be 1. Because we'll just assume that we will never get negative numbers. Now, if we do, we could raise an error. We could say this is invalid. But again, for our purposes, we're just going to assume 1, and people won't give us negative numbers. All right, so the base case then is when you reach 1, I don't have anything else to do. I'm not going to take 1 and multiply it by 0, and then every answer would be 0. So if I've got the 1, I'm done. So then what does factorial 4 look like? Well, if I want to solve factorial 4, what I need to do is solve for factorial 3, which then I need to resolve for factorial 2, which then in turn resolves for factorial 1. So if I take 4 times the result of factorial 3, which is essentially 3 times the result of factorial 2, which is essentially 2 times the result of factorial 1, which returns 1, then I've got the problem. Um, Maybe you saw this right away. This is a relatively simple problem. Maybe you didn't, and that's okay too. For some people, it's easier to work from the big to the small. For other people, it's easier to work from small to the big. So one other way to look at this is, how do I sort a list of one item? Well, it is sorted. I'm done. I return it back to you. So how do I sort a list of 2 items? Well, I put those 2 in order. Okay, so how do you sort a list of 3 items? Well, if I sort the list of 2 items and then I add then the third item, then wait, yeah, that might work. I can just do one item at a time, right? I can integrate one. Now, sorting is a very complicated problem, and you'll learn about that at some point in the future. We're not going to deal with anything like that in this class, but that's the different strategies you can take on. So let's talk about that factorial we just ran to. So the code for this is insanely simple. So factorial, we have some starting point. If that starting point is less than 2, okay, so that handles all of our error cases. I could say if the start is equal to 1, return 1. I could do that, but what happens if 0 is past it? What happens if -1's passed in? Well, that means we would be recursing and we wouldn't skip that. So often it's easier to use less than as a criteria than equals directly, because then if you end up in that error case, then you don't end up with a code that runs forever, essentially. We're not going to worry about that too much here. But again, there's the base case. And beyond that base case, right here of if it's, I could say less than or equal to 1. I just said less than 2, save myself a little bit of typing. There's the base case. If it's not the base case, then I have the recursive case, which is I take that number that I started with and multiply it by the factorial of the one below it. So 4 factorial is the results of 4 times 3 factorial, which then again recurses, and I end up with this structure right here where I went one down at a time. All right, and then when I reach the bottom, I return 1, and then that returns 1 back here, and I say 2 times 1, it returns that value, and then I say 3 times 1, and so on and so forth. So recursion has this dive down until you get an answer, and then take that answer and use it until you get back up to the start. And that's how recursion, that's how recursion makes the magic happen. So let's expand this out to a different one. Let's do a power function or an exponent function. So if I said I have a power which is some base to a power, for example, 5 to the third power. So that's 5 times 5 times 5, which is 125, or 2 to the fourth power, 2 times 2 times 2 times 2, which is 16. So how would you do this one? So here's what I want you to do. I want you to, ignore the fact that it just popped up. Take a second and think about, can you identify the base case? And then from that base case, do you think you can identify the steps to recurse to it? And is there an error case or invalid cases, and how would you handle those? So go ahead and take a moment, maybe pause it and do that. Okay, maybe you've taken a shot. So I just want to help you identify these things. So let's think about this. What is the base case? Well, if I say something is to the negative power, I'm going to treat those as something that's going to be out of scope for now. All right. Yes, you could theoretically do that because then you just kind of are dividing, instead of multiplying. But we're going to treat that out of scope for sake of simplicity. So the base case could be to the 0th power. So what is something to the 0th power? Well, it's 1. Then what's something to the 1st power? Well, it's it times itself. And what's something to the 2nd power? Well, it's it times itself 2 times. So again, in looping, I could just say multiply itself by loop that number of time and multiply it by itself. But let's look at this code, and this is a strategy I can go take on. So base and power. So if the power is less than 0, negative, we're just going to not deal with that for now. We're going to return none. That's something that we can do in Python. Just say I didn't come up with an answer for that. I could come through and add code to make that happen later on. I'm just not worried about it now. Keep it simple. If the power is equal to 0, we return 1. Right? So anything times 1 is itself. So that means we can deal with it. Now, if we somehow mess up and we get to a negative number, then we would have 0 times none, and we would end up with being an error. And so that's fine. We would end up with an error, but at least we wouldn't be given a false answer. We wouldn't be given a wrong answer. If your code's going to fail, it's better for it to truly fail than to give a seemingly correct but wrong answer. That's just a strategy in coding right there. Not related to recursion, but true everywhere. All right, so if it's greater than 0, the power greater than 0, then I take the base and multiply it times the 1 less than power. So if I said 3 to the 1, well, it's not less than 0. The power is not less than 0. It's not 0. So I'd say I'd return the results of 3 times the exponent, recursive call to myself, of 3 to the 0th power, which will then return 1. So 3 times 1 is 3. And thus if I have 2, I'm recursing through. I'm calling 3 times 3 times 1. If I do the power of 3, 3 times 3 times 3 times 1. Um, so in this case, the the recursion, uses this power of zero. You might be tempted to say, like, well, if it's one, I don't need to call it again and have a call to multiply it by one again. And that's true, but then I have to have an if statement that checks for zero because the user might call zero. I can pass in something to the power of zero. So sometimes in recursion, there's a certain inefficiency in you have one extra call at the end that you could maybe prevent in some cases, but then you don't have to have the extra check. So there's a lot of trade-offs. You're going to see different ways of tackling this. All right. Um, so at this point, these examples, I've been trying to just get you to think in terms of recursion. I've been just trying to get you to analyze that. And I wanted to show you the code that results from that. From this point on, the expectation is you're going to move into building some code. And so you might want to go work on some of these examples right now and follow through them and maybe work on some of the coding examples that'll come up as well. Um, but there is one more video on a complicated one that you might want to go and tackle at some point. Now, I'll tell you here, the Hanoi problem of towers of Hanoi is a very classic recursion problem. You don't have to do it, but if you're a computer scientist or really want to, challenge yourself, it is fun to see how powerful recursion can be when the problem is fundamentally recursive, and I'll recommend that you go and check that one out.